Okay, so this is the last section that we're going to cover. It's just a short topic, but I want to explain the general idea, and then I'll show you a couple examples, maybe two. Anyway, so yeah, so we'll be using integrals and calculus to calculate volume of shapes, different shapes. Let me just explain maybe the idea, and then we'll do those examples. Okay, so let's say we have a curve. Okay, something like this. We'll be actually calculating in a moment something similar. But for now, let's just say this is y equals f of x. And we'll take that curve and we'll rotate it about the x-axis. Alright, so this is x-axis, this is y-axis. And we'll take the curve and basically rotate it like this, right, around that x-axis. So let's do that. Alright, so if I do that, I'll have that second, right, bottom curve over here, and this will create a volume, right? So I didn't limit that curve in any way, right? So we'll have some boundaries, right? So we'll be calculating that volume between, say, A and B, right? So this is B. Okay, so yeah, so I hope you understand. So this is, right? So this is a like a three-dimensional figure. Let me draw. Okay, maybe now you can see it better. Okay, so we'll be only looking at that volume and that figure from A to B. Okay, so if we looked at that figure from the top, we would see a circle. Right, so let me draw that circle. Right, so I'm looking at that cone, and it's not really a cone, right? But we could call it a cone. And that cone would have a radius, right? So that's some radius, right? So that radius will be here. Okay, so that's that radius. And of course, right, if it's a circle, then we could very easily calculate the area of that circle, right? So that area, the circle would be pi r squared. Okay. But of course, we're not interested in area, right? We're interested in volume. So what we will do, we will form a disk. Right, so I'm going to draw it here. And the shape, that's a disk. Okay, has some kind of thickness, right? That's height. Alright, so this is a disk. Or, I hope you, again, right? I'm not happy with my pictures. Let me try again. Okay, I'll try to do. It probably has some, there's some function I could use that would make a nice disk, but anyway, I don't know if it's better, but I hope the idea, right? The point is so that you understand what's happening. Okay, so I'm going to redraw the disk over here, a little bit lower. Okay. So it's a disk, right? Right now you can see that it's basically a cylinder, right? So that cylinder has radius. Yeah, it's the same radius. I mean, not the same, but... Okay, so now to calculate the volume of the disk, right, I would simply take the area, right, and multiply it by height of that disk. So this is going to be h. Right, so A times h, or right, we could use that formula for area, pi r squared times h. Okay, so this is just one disk, but what we can do, we can fill this cone, right, or divide this cone into a bunch of little disks, right, whose volume is going to be changing, right? If I'm moving to the left, right, the volumes of those disks will be smaller. When I'm moving to the right, right, I'll have a bunch of those disks here, right? That volume will be changing with the radius, right? The bigger the radius, the bigger the volume of those disks, right? And of course, we're in calculus, so what we'll have infinite number of those disks. But for now, let me just write it as a sum. Okay, so I'm going to take a sum from, from 1 to some number n, and we'll basically take, right, the volumes of those disks. We'll simply add them up, right? So times h. Okay, so that's basically the idea, right? And then, of course, yeah, we're just going to write it in a slightly different way. And as I said, right, we'll use calculus because we want to have, right, introduce the idea of infinite number of those disks, right? So that n, the number of those disks, will be approaching, just like calculating that area before, and a couple lectures before. So that n will be approaching infinity. Okay, then I have that summation. So again, from 1 to n. And then instead of just writing that pi r square, I'm going to write a. Right? So it's going to be a function here, because that radius, right? This radius here, and it's going to be changing according to this function, to y equals f of x. Okay. So that's one way of writing it, and then, right, we have that idea of, so this is the area. Now we need to multiply it by that h. So, right, we're going to call that h in this case delta x. Okay, and just like with that concept of the area, right, I'm going to use that integral from a to b. Right, I have the area a of x times dx. Okay, and of course area is that radius squared times pi. Okay, so it's going, finally that formula for calculating those volumes will look like this. So we'll have pi, which is a constant, so we'll be able to take it outside. Then I have that function according to which the radius changes, right? R squared dx. All right, so that's the formula for calculating volume using the disk method. All right, so one more time. We're using, right, integral, the idea of those number of those disks approaching infinity, and we're simply adding the infinite number of those disks, right? This is the volume of, right, in a sense, a disk, right? And there's infinite number of those. Okay, so let's do an example, and you'll see how it works. So example 1. So calculate volume. Of a figure formed or created, that's right, maybe formed by rotating a curve y equals, right? So here we have a specific function, y equals square root of x, and we're rotating it about the x-axis. And we're going to calculate it from 1 to 4. So those boundaries of integration will be 1 and 4. Okay, so in calculus 2, you'll be calculating the the volumes of figures that are infinite. Anyway, yeah, so let's just write a little note. So radius, so note. Radius is changing according to y equals square root of x. Okay, so now the volume, let's write that formula will be in definite integral from 1 to 4. Oh, maybe before we actually start solving the problem, let's graph it. Okay, so y equals square root of x, that will be our curve, our function. And we're supposed to calculate it from 1 to 4. Right? So this is 1, say this is 4. Then the section, right? So that's going to be our section of the curve that will be rotating. And then it's going to, okay, I'm trying to make it nice. Right, so that's the shape. This is 4, and of course I made it a little bit too long, this one. And so we need to stop here. Okay. Right, so that's that cross section. Here is the radius. And then we could have, I don't know, a little disc here, just kind of to illustrate what's happening. And then again, and we have radius. This is the thickness, right, dx. And yeah, let's write that formula. Thickness. And the formula looks like this, right? So that volume is a definite integral from 1 to 4. And then, yeah, we have that pi r squared, right? And then dx. Okay, so r squared, and it's that function, or r. Right, so we have definite integral from 1 to 4 pi, and now I'm plugging that, right, our function, right there. So square root of x, and this is squared, and it's dx. Alright, so finally I'll take that pi out, right? I factor it out because it's a constant. from 1 to 4, and then we have just x dx. Alright, so now I hope this is an easy integral to do. So we have half x squared, and here are those endpoints 1 to 4. Okay, so let's plug in those endpoints. So we have pi. And now, yeah, just a little bit of arithmetic. So half 4 squared. Okay, then minus half, and this time is 1 squared. Okay, so it's looks like 16. Half of that is 8. So we have pi times 8. Something's missing, this parenthesis. 8 minus half. Okay, so the answer is 15 pi over 2. Yeah, so that's one example. I have let me do one more, and that is going to be it. Okay, so example 2. Yeah, and yeah, I'll give you a couple of problems for homework as well. So this time I'm not going to write this sentence, just calculate volume. I'm not going to write the full sentence. The function is square root of sine x. And the boundaries of integration is, so from 0 to pi. Okay, so let's start with the picture. Okay, so here's the x-axis. And that curve basically looks like this. I don't know, I haven't graphed it, but this is what I have in my notes. So this is pi. And now, right, we rotate this curve again about the x-axis, right? And we will get this shape, this, I don't know, football. And then again, the idea is, right, we divide it into a bunch of those disks, infinite number of them. Here's one of them. And yeah, so let's write the formula for volume. Again, right, so I have from 0 to pi. Then I have pi r squared, right? So just writing the formula using that r dx. Now I'll plug in the function, so from 0 to pi. So we'll have pi. Now I have that sine square. It's not sine square, square root of sine. Now this is squared dx. Right, so it's pretty convenient that I have that square root. Right, without it, calculating integral of sine square would be difficult. But this way, right, we just end up with sine. So I have pi. Again, I took it out from 0 to pi. Now it's just sine x and dx. Okay, so integral of, or antiderivative of sine x is negative cosine x. So we have negative cosine x, and we're supposed to integrate it from 0 to pi. Okay, so just I'm missing the pi in the front. Okay, so yeah, cosine of pi, cosine of 0 is 1, cosine of pi is negative 1, and we get the final answer is 2 pi. Okay, so that's it. As I said, yeah, I have a couple of practice problems, but let's just do, yeah, I'm just going to have you do some homework. All right, so that's it.